It's time for the tumor problem, another application of differential equations. Here is the story of something that is related to like growth, or like a tumor, sadly. If you have something that grows, it usually is proportional to the size of the tumor. So for example, if that tumor here is this size and it grows, say 10% per time, I'm going to take roughly a 10% chunk and that gets added on. And that goes the same for if it's a smaller tumor, 10% of it will be added on. So the size or the growth is related to the initial size of the object. And so 10% for a large tumor is a larger piece than 10% for a small tumor, but they are proportional. So this is a differential equation application. Write a differential equation satisfied by S, the size of the tumor as a function of time. This means that the rate of the size of that tumor with respect to time is proportional. That means there's some value multiplied by the size. It could be 10%, it could be minus 2%, something like that. That is the differential equation. It's an equation that's expressed as a rate of change. Part B, find the general solution. So this should be, this one is nice to do because this is a separable differential equation. You should know the drill by now. You separate the variables into big S's and T's. You integrate on both sides. This is nice. There's no many U subs to contend with. We get the natural log of S equals KT plus some constant. We take E and we raise it to both sides of the equation. That means we liberate S equals E to the KT plus C, also known as C E to the KT, because E to the KT plus C can be written as E to the KT times E to the C, and E to the C is just a constant. We haven't broken any rules yet of math because we don't know any initial conditions. This is the general solution to this equation. Differential equations. The answer to differential equations are functions, classes of functions. There's an infinite number of these. Once though we see that the tumor was 5 millimeters across at time 0, we're locked in to finding what that initial value is. So in part C, we know that S of 0, so at time 0 we're looking at 5. So whenever you see a T, that gets you 0, and an S, that gives you 5. So 5 equals C E to the K times 0, or E to the 0. This helps you find that C is equal to 5. That makes sense because it's at time 0, the E vanishes and we have 5. So S equals 5 E to the KT. KT. This is a specific class for a tumor that has an initial value of 5 millimeters. We also know in this part D that at 3 minutes? Sorry, at t equals 3, it doesn't say, maybe it's years, months. At t equals 3, S equals 8. So we can go even further and take this equation and make it 8 equals 5 times E to the K times 3. That means we can kind of solve for K to find the growth rate. That means 8/5 equals E to the 3K. We want to liberate that K. We take natural log of both sides. And the natural log of e to some power is nice because that just liberates the 3k equals natural log of 8/5. K becomes the natural log of 8/5 all over 3. You need a calculator for that. That is about 0.1567. With that information, we can write now the very specific equation. S, size of that tumor, is 5e to the 0.1567 t. Done.